All right, so I'm going to review the commutation relations for the Lorentz group and the relation to a rotation group. What we saw was that basically the ordinary rotation operators these are in natural units, so h bar and c equals 1. The commutation relations for the boosts, this of course is the ordinary commutation relations of the rotation group SO3. Now the boosts, of course, are boosts in the x, y, or z direction. So the boosts are vectors, and so under a rotation, they behave like any vector. Any three-dimensional vector under a rotation does this. But then the strange part of the boosts is that their commutator is minus I epsilon jk, which is, I don't know, I suppose that Witten looks at this and sees when it becomes transparent, but it's not transparent to me. Anyway, the enormous advantage, well, let me just say what the ordinary Lorentz transformation is. It's e to the minus I theta dot j minus I lambda dot k. So these are the general Lorentz transformations, which are rotations about an angle theta and boosts in the lambda direction. The remarkable thing, though, is that if we define the operators JL plus or minus as a half the angular momentum part plus or minus I times the boost part, then these J plus or minuses obey very nice commutation relations. J plus I, J plus J, I epsilon I j k, J plus K, J minus I, J minus J, I epsilon I j k, J minus K, and best of all, Ji plus Jj minus 0. So the remarkable thing is that the operators, which are the generators of the Lorentz transformations, obey the commutation relations of angular momentum. So you have two angular momenta. From the point of view of algebra, you have two angular momenta that then commute. And moreover, we can write JL as JL plus JL minus, and KL as 1 over I times JL plus minus JL minus.
Hey, Kevin.
Yeah. You want to get a quick coffee?
No, I'll let you go. I'm sorry.
All right, so these are then the original operators, the original generators of the Lorentz group are these Hermitian generators and these anti-Hermitian generators. So the general Lorentz transformation then is djj prime, let us say theta and lambda. This would be e to the minus I theta dot j minus I lambda dot k. And the j's, of course, are Hermitian, so this part is unitary, but the k's are anti-Hermitian, so this part is not unitary. And this is the boost part. But now if we rewrite j in this way and k in that way, then we have a structure here in which we can group the j pluses together and the j minuses together. Those two things commute with each other, and we can rewrite this as e to the minus I theta minus lambda dot j plus, and then e to the minus I theta plus lambda dot j minus. So we can write it this way. And now the algebra of these things is what we learned when we were students in quantum mechanics classes. Of course, we should have learned it in the bloody math course, but God forbid the mathematicians would ever teach us anything useful. In fact, physicists had to invent all of mathematics. All right, anyway, these guys here are the matrices that we learned about in quantum mechanics because they obey these SU2 related. These is the algebra of SU2 or SO3. And consequently, these guys are, how shall I say it? Maybe over here. These guys are, these are both, well, over here, since I have a J here, what does that mean? That means that these guys are 2J plus 1 by 2J plus 1 dimensional matrices. In fact, Hermitian matrices, and there are 3 of them. And these guys, let's see, I should have a prime here, shouldn't I? So let's, yeah, that's right. What I'm saying here is that these guys are 2J prime plus 1 by 2J prime plus 1 dimensional matrices. So that's what this J prime is. And under Lorentz transformation, a field, so here's the Lorentz transformation, is a field that transforms under JJ prime, and it has, this one says what kind of field is it is, and this one says which components of that field. So M runs from 1 to 2J plus 1, and prime runs from 1 to 2J prime plus 1. And then we have a U-inverse of that. These guys are unitary matrices, but infinite dimensional. They're the operators. And then this is a DJ0 MM double prime of L inverse, and then a D0 J prime, M prime, M triple prime of L inverse times psi of J and J prime, M double prime, and triple prime of Lx. So that's how fields transform. And now, of course, we're mainly concerned with spin 1/2, spin 0, spin 1, maybe spin 2 for gravity. spin 3/2 for the gravitino. And so what we have here, this is basically if we look at the spin of the particle, then this one has spin j, this one has spin j prime. And so this field then can describe particles of spin going from j minus j prime to j minus j prime plus 1 on up to j plus j prime. That's the standard rules we learn in quantum mechanics for the addition of any given length. The simplest case is when j is 1/2 and j prime is 0. And that's basically the left-handed case. So now we want to be careful about light. We don't want any huge amount of sunlight because when it does, the camera adjusts to the bright light and goes down, and you can't see the writing on the board. Okay, so now what we've got is d 1/2 0 of theta and lambda, and this turns out to be e to the minus I theta dot sigma over 2 minus lambda dot sigma over 2. Or equivalently, it's e to the minus z dot sigma over 2. So sigma over 2 is, let us say, it plays the role of j plus here. And j plus for j equal to 1/2. And z is a complex 3 vector in which the real part is lambda. In other words, z is equal to lambda plus I theta. Okay. And, okay, so this is the standard left hand, spin 1/2 left-handed spinner. This representation, you can multiply these out because these are just 2x2 matrices. And it turns out that if we're talking about d 1/2 0, no rotation, just a boost of angle alpha in a sense, or rapidity alpha in the p hat direction, so that lambda is alpha p hat. So we're setting, in this we're setting theta equal to 0, lambda equal alpha p hat. And this thing is p0 plus m minus p dot sigma over a square root of 2m p0 plus m. You guys want to get on to tensors, right?
Yes.
So, no, it's not that I have to skip a lot of stuff, but I think maybe I can just refer to the textbook for the microscopic stuff.
Okay.
In particular, if we define a 4-vector like this, minus the identity, 2x2 identity, and then the 3-vector sigma, what happens is this d adjoint of 1/2 0 for a general Lorentz transformation. In fact, now I see I used the wrong notation. Let me get one of these erasers. So if we call this thing SA, this 4 vector, then dl on SA, d 1/2 0, and this is the adjoint of the matrix, L is equal to LAB SB. So this thing transforms to 4 vector, and the result of that is, well, first of all, how does a massless field spin 1/2 transform? A left-handed spinner goes this way. L C of X, U inverse of L, is then D 1/2 0 on L inverse C of LX. So that's how it transforms. And then what you can see is that an action density that's invariant and left-handed is I C dagger of X time derivative on I, the 2x2 identity, minus divergence got it into Pauli matrices on sigma. Well, what you can show, and it's shown in detail in the book, is that since this guy transforms this way, this thing is Lorentz invariant. And what's happening here is that under the Lorentz transformation, because you go from C of X to C of LX, where that's the Lorentz transformation, when you change from ordinary derivatives to derivatives with respect to LX, this guy transforms in a certain way, but I and sigma transform the other way, so the whole thing's invariant. That's basically how it works. And of course, if instead you're talking about Z0 1/2, it's all essentially the same except for a minus sign here and there. The corresponding right-handed field, right-handed action, the only difference is that instead of a minus, there's a plus here. So the action for the left-handed field is minus, so LR minus plus. There's also this business of the Majorana mass term, and this comes up a great deal in neutrino physics, so I might as well mention what it's like, or what it is. And the basic idea is you have an M, and you have a psi dagger, a sigma 2, and let us say psi complex conjugate. And now, how does psi transform? Well, psi transforms this way as e to the minus z dot sigma. So this thing prime is m c dagger e to the minus z dot sigma over 2 dagger sigma 2, and then e to the minus z dot sigma over 2 c star. Star being you complex conjugate all the numbers. We're just talking about numbers there. If you have operators, then you Hermitian adjoint them. But you don't, we've got this focus in physics departments. It's one of our we have several fetishes in physics departments. In astronomy departments, they all speak Latin. But in physics departments, we've got to have this vector like this on the right, like that on the left. And all right, let's see how this works. This will be m. By the way, my left arm is down. When the left arm is down, you've got to watch the mistakes, okay? So, C dagger. All right, the adjoint of that. Well, what's going to happen here is that you're going to get the adjoint of the Pauli matrices, and then you're going to complex conjugate that. So this is minus z star dot sigma over 2, because the Pauli matrices themselves are Hermitian. Then we've got a sigma 2. And now what happens here? We're just complex conjugating everything. So this is e to the minus z star, but now it's sigma star. In sigma star, it's sigma 1 minus sigma 2, sigma 3 over z star. Because sigma 2 is imaginary. In physics, you don't have to remember very much. But you have to, it's useful to know what the Pauli means. Because these days, you're sitting at a desk, you just Google everything, and it's right there. So, in a sense, you don't have to remember anything. All right, now, if we bring the sigma 2 through here, it doesn't affect this sigma 2, but it flips these two signs. Okay. So this is equal to m c dagger e to the minus z star dot sigma over 2. E, so we get a minus and a minus, so everybody's minus, we make this a plus. Z star dot sigma over 2. Sigma 2 c star. Now you see these guys are the same, they cancel. And so this is equal to m c dagger sigma 2 c star. So that's the Majorana mass term. And you can do the same thing for the right-handed fields. Clearly the right-hand, oh, I didn't say what the operator is for the right-handed group. So let me get it. I think it's just, so this is the left-handed one. The right-handed one is simply e to the z star dot sigma over 2. So the difference between these two is minus z and plus z star. So this is d 0 1/2 theta lambda is this, with the same identification of this, that is to say that, yeah, okay, it's the same thing. All right, so you can do the same thing for the right-handed field, and in fact, you might say, well, what's the difference between that Majorana mass term and Dirac mass term? Dirac mass term is just two Majorana mass terms. By the way, I'm starting to think that all this emphasis on these spin 1/2 representations, I mean these two-dimensional representations, is excessive. So let's now go to the Dirac representation. What we can do is we can say that we just are putting together in the Dirac representation a left-handed spinner. So we have the upper two components of the left-handed, bottom two of the right-handed. And what you can see here is that the spin part is minus I theta here, and it's also minus I theta there. So the spin part is the same. That's why we have the same sigmas. On the other hand, the boost part is I over 2 minus sigma 0, 0, sigma. So it's the boost part that distinguishes the right and left-handed two-component spins. Now the remarkable thing, discovered originally by Dirac, who seems as though he's discovered everything. Everything important. I mean, the other people discovered the unimportant things. What he found out is you can take these 4x4 matrices, which he wrote as gamma matrices for some reason, Okay, this is the 4x4 identity matrix. A to AB is just our standard flat space metric. It's minus 1, 1, 1, 1. Okay, so minus on the time components, 1 on the space components. Of course, this choice is not respected. Half the time it's the other way. It's like unlike in the Iowa caucuses where Hillary got all of the coin tosses, because of course the coins are supplied by the Democratic Party officially. In the case of physics departments, half faculty go this way, the other half of the faculty go 1, -1, -1, -1. So it's one of the upsetting things. Okay, now here's the truly remarkable thing. There are a number of remarkable things. Jij is epsilon ijk jk. So we can rename, this is sort of a baptism, I should have the eraser here that's still wet and shake it to baptize this operator here. But this is in other words, we're going to call, instead of J3, we're going to call it J12. And here's the remarkable thing, and we're going to take the boost operators, we're going to call them J0J, and I'm going to call that just KJ. All right, now here's the remarkable thing. These are the 6 generators of the Lorentz group. And we can write them in this way. JAB equals minus I over 4, the commutator of the gamma matrices. This is called Clifford algebra. And anyway, it's really just remarkable. And the remarkable thing about it is it works in any number of dimensions. So in other words, we're talking about 1 time and 3 space. We could be talking about 1 time and 29 space. And we could still find gamma matrices that anti-commute with each other, satisfy this relation. We would then define the generators of the Lorentz group, SO128, say, in this way, and these J's would obey the commutation relations of angular momentum, which in fact are IJAB, JCD is equal to A to BC JAB minus A to AC JBD minus A to DA JCB plus A to DB JCA. And just a word about eta. Eta is obviously symmetric. On the other hand, the J's, defined as they are as commutators, are obviously anti-symmetric. Okay. So you can screw around with this. If you call this dB, then you put a plus sign here. And you can make this AD instead of DA. You don't need to change any sign. So there are many ways of writing this, but these are the commutation relations of the Lorentz group. Now, when I discussed the Lorentz group originally, I discussed it in a much simpler notation, and maybe I should remind you what it was. It was basically, this is actually nothing more than omega transpose is minus eta omega eta, where here L is I plus So in other words, this, all we're really talking about is this, and there's 6 different omegas, and they all have to be like that. And this condition here basically says that that if you, under transposition, the time and space elements of omega change sign, whereas the time, space, and space-time ones don't. And so this is the simple, clear essence of it. This is the dressed-up version. Okay. In any event, the remarkable thing is that you can do all these things in terms of these Dirac matrices. The nice Dirac matrices for particle physics are gamma 0 minus I, 0, 1, 1, 0, and gamma vector is minus I, 0, sigma, minus sigma 0. So those are the gamma matrices. And what Dirac did was he wrote these in the form C zeta, and then if you combine the 2 actions for a massless left-handed spinner and massless right-handed spinner together, you have an action which is minus psi bar gamma A dA plus m psi, and the corresponding writes this as, or wrote this as, d slash plus m psi. And in fact, I learned, talking with Anthony Z over the last few days, that Feynman introduced this slash notation very, very early. It was back when people were puzzling over whether Schwinger's quantum microdynamics was the same as Feynman, and Dyson eventually showed that the 2 were the same. And people couldn't figure out. They spent many time. People in Chicago gathered together and tried to figure out what Feynman was saying, and the only thing they could remember was that he had this funny slash. By the way, in LaTeX, you say, I think, use package slash, and then you just say backslash slash curly bracket, whatever it is, curly bracket, and the slash comes out. Pretty good on this. Anyway, that's that. Well, what is psi bar? Psi bar is I psi dagger gamma 0. And the Dirac mass term is, well, let me toss in the Dirac mass term. Well, the Dirac mass term is just minus m psi bar psi. And I was saying that this was 2 Majorana mass terms. Well, I guess in a sense it is, in another sense it isn't. Anyway, the Poincaré group just adds to the J's. It just adds to the J's P's, and where P is the 4 vector H and P. So you add that together with the JAB. This gives you 10 generators. 4 here translate space-time points, and then these 6 are rotations. Well, 3 are rotations, 3 are boosts, and then you have the 3 translations. Okay, so let me now switch completely to the topic that at least one of you wanted a long time ago, and it's tensors. I think that there's a great deal of unjustified mysticism surrounding tensors, and I'm going to do my best to dispel it. First, we have to wait for this to dry, and while it's drying, I'll say a few things that in words are important, even though normally express everything in terms of equations, but words are also useful. The basic thing is you want to distinguish between points and coordinates. And so the way I think of it is that points are physical and coordinates are metaphysical. Points are unique. Coordinates are anything but unique. And in fact, one of the ideas of general relativity, in some sense the principal idea of general relativity, and also of gauge theory, is that you should be able to change your coordinates as much as possible. And I think it was Eddington who said that the reason why this is the case is that, who's to say what the right coordinate system is? And, that's a very persuasive statement. And so that's the first thing. In other words, we'll be thinking in general of some kind of a curved manifold, and by manifold, what we really... All right, let me back up a bit. If we have a point on a manifold, on any surface, let's say, that point on the surface we can also think of as a point in an embedding space that's just ordinary Euclidean space. Lorentz. And in fact, there was a mathematician named Whitney who proved an embedding theorem, which is that if you have a smooth manifold in, say, 4 dimensions, you can always embed it in 8-dimensional Euclidean space. And we, of course, have a simple example of that, namely that if you have, here's a curved manifold, we can embed it in flat 3 space. We're all familiar with that. And the surface of the sphere is in the moment where we live in almost flat 3-dimensional space, and we can imagine this, we always think of a sphere as an ordinary sphere in 3-dimensional space. And one of the triumphs of differential geometry in the past, say, 100 years is that mathematicians figured out how to give a description of manifolds that are a description that's intrinsic to the manifold and doesn't require embedding. And of course, one of the reasons they did that was that they didn't know about Whitney's embedding theorem, because it was proven, I think, I forget when, but it's a lot more recent than general relativity. And I think the easy way to think about all these things is to imagine the manifolds, whatever they are, embedded in a flat Euclidean space of a sufficient number of dimensions. And it may even be true that the reason why extra dimensions are showing up in theoretical physics may simply be because we really do live in a world where our space-time, according to general relativity, is curved, and well, if it's curved in a bigger space-time of, let us say, 8 dimensions, and you could add dimensions, and then, you know, if you can embed it in 8, you can embed it in 9, and moreover, you can, what Kaluza showed about 100 years ago was that, almost 100 years ago, is that if you did general relativity in 5 dimensions, you get electromagnetism for free, and you also get a scalar field in it. But I don't want to go in that direction. Instead, let me just say that let's just think about any smooth space. If we look at it on a small scale, it looks like Euclidean space. And for example, this 2-dimensional thing, okay, I've curved it, but if you look at it on a scale of nanometers, it's perfectly flat. And so that's basically the idea of a manifold, namely that you can map the, first of all, that you can map, first of all, on the manifold, each point on the manifold we can describe by coordinates. And the coordinates typically are coordinates on the manifold. So in this case, we have 2 coordinates for example, you could imagine if this were graph paper, then we'd obviously have coordinates on this. But then when we curve it, or crumple it, or even do that to it, these, what do I want to say? These coordinates if we then, so we can crumple it, if we then magnify everything, everything becomes locally flat, and it looks like ordinary 2-dimensional Euclidean space. Each little part of the crumpled thing. Anyway, so that's the idea of a manifold that you can.
Is there like a property that's constant across the manifold's surface? I mean, like if you were talking about a sphere, it would be a constant radius.
Yeah,
like R would be.
Right. Not only that, but with a sphere, you have the curvature is the same everywhere on the surface.
Okay, but so like a manifold would have some parameter that's.
I think the only thing, no, manifold is very general. So the only thing is that locally it looks like Euclidean space.
Okay.
So in other words, you can have a function that's 1-to-1 and invertible and so forth between Euclidean space and any small patch on the manifold. And then as you go to another patch, you have a different map from Euclidean space to that little patch.
Okay.
That's the idea. Now, when the space is curved, sometimes the coordinates can be, normally the coordinates and the points are, well, once you adopt a set of coordinates, the relationship between the coordinates and the points are basically unique. On the other hand, for many curved spaces, there are some points that aren't unique. For example, again, depending on the coordinates on a sphere that we, or just on the Earth, latitude and longitude, and or on a sphere we could think of theta as the polar angle, phi as the azimuthal angle. Well, there at the North Pole, phi is not, theta is 0, but any phi can be the same because they're all, well, it's obvious that they're all. So the idea is then that that the 2-dimensional coordinates for the North Pole aren't the same in the standard coordinate system, but if we instead do a coordinate system where the polar axis is along equator, from one side to the other of the equator, then we have good coordinates. We have unique coordinates for the North and South Pole, but not so good for these 2 points on the equator. So there is that aspect that you need more than one coordinate system in general to have sensible coordinates for every point. You need to use 2 coordinate systems. And, okay, so we're almost out of time, but the blackboard at least is dry. And so I want to emphasize now the two ideas that are extremely simple and that otherwise can be confusing. So here we're going to be talking about the coordinates of a point, and we might have another set of coordinates of the same point. And what is a scalar? What bothers me about for me, the hardest part of the concept of scalar is whether this is an E or an A. Anyway, it's a quantity such that in all coordinate systems it's the same. And if the thing is a field, then a scalar field does this. That is to say, in arbitrary coordinates x prime, the scalar b prime at x prime is the same as p of x. Okay, that's called a scalar field. Now, if we then think about changes in coordinates, dx prime is the sum partial x prime I partial xj dxj. This is just a chain rule where you sum, and this can be in n dimensions. This is what defines contravariant coordinates, or contravariant vectors. And the idea is that any vector that transforms this way, a prime I, is, let me use the summation convention, okay, so we have to write all these crazy sums. Partial x prime I, partial x j, aj. So in other words, this imitates how the differentials transform. This is then called a contravariant vector, and if it depends upon space, time, or the coordinates, then it's called a contravariant vector field. Covariant, it's equally simple. The derivative with respect to xi prime is partial xj partial xi prime partial xj. So the chain rule for differentiating. So that's how derivatives transform. Any vector that transforms this way is said to be a covariant vector. And if it depends upon space, then it's a covariant vector field. So these things, so that basically is it. And moreover, you can generalize this. If you have something, for example, that goes like this, Mij of x prime is partial x, let me make this a k, partial xj, partial x prime I, partial xl, partial x prime k, times m jl of x, then this is a rank 2 covariant tensor field. fact, the metric of gravity, space-time, g mu of x is one of these. On the other hand, if it does everything the other way, like the differential, then it's a contravariant field. So in other words, if we had something t, we said t prime of x prime, and we want upper indices here. So let us say ij. This would, I gotta know where to put them. All right, so this is partial x prime I, partial x prime j, partial x k, partial x l, t k l. Okay, so this would be a covariant, contravariant, second order field, tensor field. Okay, and notice here that I'm talking about two different coordinate systems. They're arbitrary descriptions of the points on the manifold, just so that they, basically make sense in the way we were describing. So a general coordinate transformation is one in which you go from here to there. How do things transform in a general coordinate transformation? We already know the whole story. It's just that they go this way. The differentials go that way. The derivatives go this way. Things that imitate the differentials or the derivatives are called contravariant or covariant things. Whatever. Tensors are rank whatever. 1 is vector, 2 is rank 2, and so forth. And you can have an arbitrary number. You could have something that was t I j k l, and then if we describe how that would go, we would have 4 derivatives here. 2 of them would be this way, 2 of them would be that way. Okay, I think that's enough for today. So we can